Today we're going to be continuing with chapter 12. Again, we've done fundamental counting principle. We did permutations the other day, and today we are doing combinations. Okay, so combinations. Now, the other day we learned about permutations, where order matters and there's no repetition. Today we're going to be talking about combinations, where order does not matter and there's no repetition. Okay, so again, just a little reminder. Permutation, order matters, and no repeats. Those are the two main things you need. Order matters and no repeats. Combination, order does not matter, and again, still no repeats. Today I'm going to go through the notes first, and then we're going to go back and do the classwork. Let me just rewrite for you guys the formula for permutation. So permutation, n items taken are at a time, okay? And again, this is when we're trying to order them. So we're going to get r of them and put them in order. And the formula for that is NPR is equal to n factorial over. So remember, we are choosing r of them. We do not care about the ones we're not picking. That's n minus r factorial. Those are the ones that we are taking that are not going to be chosen. And just so you understand, this does two things. What it does is it's going to get our items into a group of R, and it orders those R items. Okay, so it wants all the ways we can choose R of the items and get them into groups of R and order those R things. Now, example, 5p3 is equal to 5 factorial over the ones we didn't pick, which we chose 3 out of 5, which means 2 did not get picked. So we're going to take out all the ways we can arrange those 2 items. And that's going to equal 60 when I put that into my calculator. And what this does is it gives me how many groups of 3 can I get out of 5 items. Okay, and then it orders those 3 in the group. Okay, so it's going to take from 5, it's going to get them into groups of 3 and then order those 3 items in the group. And that would be 60 different ways that that can happen. Now, how a combination is different is like a permutation, I'm going to get them into the groups of R items, but I do not want the order of those R things. So a combination is going to be groups of R items Okay, again, if I'm talking about taking out from the N R of them, so groups of R items chosen from N total items without order. So let me write that formula. I'm going to write it in a few different ways. So NCR, I usually read N choose R, is equal to NPR. So I want us to write it, understand how it is related to a permutation. A combination is the permutation of the same amount of items for the same amount of spots. Again, this groups these into groups of R and orders those R items. I want them in the group of R. I do not want the order of R items. So how do I get rid of the order of R items? R factorial is the order of those R items. So if you take the combination, a combination is equal to the permutation divided by this number R factorial. Now, another way to write it is going to be in factorial form, n factorial over. Now, on the bottom, I'm going to have two things on the bottom. The way I usually think about this is I usually take this number here, so R, and this other number is what adds with R to get me N, which is really N minus R. Now, what you'll notice is this right here. So again, combinations, N choose R, I say choose when I usually read this, N choose R is equal to your permutation divided by all the ways you can order these R items because we're dividing out the order, so R factorial. And that's equal to, in factorial form, N factorial over R factorial times N minus R factorial. And these two numbers will always add up to this top number. Okay, so let me write an example of this situation, but as a combination. So let's say I have, for example, 5 choose 3. Okay, so 5 choose 3. And that is going to be equal to 5 factorial over, and I usually start with this number, 3 factorial, and then 3 plus what gets me 5? 2, so 2 factorial. And just so you guys can see right here, this would be my permutation. That is really NP, sorry, 5 in this case. This is really 5P3, okay? It's the same thing I had up here. And then I'm dividing out the order of the 3 items. So this is getting groups of, all the different groups of 3 and ordering those 3 things. That's what this that I circled in orange is doing. And then here I'm dividing out that order because order doesn't matter for a combination. And when I do that math, I end up with 10 as my answer. So again, if you notice up here, I have 60. Down here, I have 10. This is the permutation with the same total and the same number of items I'm picking. Down here is the combination. And what you'll notice is I am really dividing out my 3 factorial. So again, this was 60 from up here divided by 3 factorial, and 3 factorial is really 6. And that's how I get my 10, just so you understand the relationship between a permutation and a combination. Now I'm going to write this formula also in another form. So N choose R, again, is equal to my permutation of the same number of total items, but in the same number of items I'm picking, over R factorial, the number of items in the group. I'm taking out their order. And again, that's equal to N factorial over R factorial times N minus R factorial. And another way to write this, you might see it in this form, where you have parentheses and you have N and R like this. This is read N choose R. So this and this are the same. You'll see it in this form when you get to integrated 3 math analysis. So let me just scooch this down. So let's say, for example, I have 5 choose 2. So again, this is really 5 choose 2, which is going to be 5 factorial over, and then again, I usually start with this number, 2 factorial, and 2 plus what gets me 5? 3. And what I want you to notice is that this one here, 5 choose 3, and this one here, 5 choose 2. See how I have 5 factorial, and then on the bottom 3 factorial times 2 factorial? Same thing here. The order of these doesn't really matter because multiplication is commutative. And so this again is going to equal 10. So that's going to give me the following situation, okay? So let me just say here, note, 5 choose 2 is equal to 5 choose 3. Now, let me do one more example like this. I'm going to write it in this type of a form as opposed to this. So again, note, if I have 10 choose 7, 10 choose 7 is going to be the same as 10 choose, well, again, what can I add with 7 to get 10? 3. So 10 choose 7 and 10 choose 3 are going to be the same. Both of them are going to be 10 factorial on top, and on bottom, this one I'd have a 7 factorial and a 3 factorial. Here I'm going to have a 3 factorial and a 7 factorial. In both cases, I'm going to have the same thing on bottom. Another example, 15 choose 10. That, for example, would be the same as 15 choose. Again, 10 plus what gets me 15? 10 plus 5. So those would be the same. And that will always be the case for any combination. Now, let's get some word problem examples. So let's say we have 40 people trying out for a soccer team. So 40 people trying out for a soccer team. And the coach will take 16 players. So coach will take 16 players. How many different teams of 16 can be made? So how many different teams of 16 can be made? Okay, so in this case, order does not matter. I'm not trying to place these 16 players on the field. I'm just trying to get a group of 16 for the team. So order does not matter. Okay, so since order does not matter, it's going to be a combination. And there's 40 choose 16. And on the homework, I want you guys to practice like I wanted you guys the other day. practice writing it in combination form and then factorial form. Or if it's a permutation, write it in permutation form and then factorial form, and then obviously give me the answer. So 40 choose 16 is going to be 40 factorial over 16 factorial times 24 factorial. And if I'm putting in my calculator like this, that's fine. But if I'm putting in my calculator in this form, you want to make sure you put parentheses around your denominator, unless you're entering it in as a fraction in the fraction mode on your graphing calculator. Okay, now the answer to that, let me just compute it out here, is 6.285 times 10 to the 10th. And when you're trying to do that again on these graphing calculators, and if you have the student Chromebooks from school, you should have a TI-84 on your toolbar that they put on for you guys. But if I'm trying to find the combination on this calculator, 2 ways to do it. I can do math, and then here it is under probability. I like to arrow backwards, and there's probability. Number 3 is combination. Number 2 is permutation. And number 4 is factorial. Or I can do alpha. Remember, alpha equal is your fraction. Alpha window gives you these options, and here's your permutation, here's your combination, here's your factorial. So I want number 8. So I want 40 choose 16. And remember, this E is really scientific notation, okay? So that's where I got that times 10 to the 10th. And that's your answer. Now, this is how many different ways I can get a group of 16 people to be on the team. If I wanted to, out of these 40 people, place them on the field, that would be a permutation, and this would be a much bigger number. Okay, quick note before we get to the next problems. Anytime you're dealing with a hand of cards is going to be a combination. So a hand of cards, like if you're playing poker or Old Maid or Go Fish, a hand of cards is a combination. You do not have to keep the cards in the order that they are given to you. You can rearrange them in your hand. So you just want to get those cards in your hand, and then you can arrange them however you want in your hand. So a hand of cards is a combination. So let's say, for example, we try the following. How many 5-card hands can I get? Now, just to make sure everyone understands, because I know not everyone is as familiar with cards as others of us. So there are 52 cards in the deck. And those 52 cards have 26 that are black, and there are 26 that are red. And the black are separated into 2 different suits. So you have 13 spades, and you have 13 clubs. Your red ones, again, are split into 2. So you have 13 diamonds, and you have 13 hearts. Okay, so, and these are your suits. There are 4 suits. And in dealing with cards, we have what we call face cards. And your face cards are your king, your queen, and your jack. Joker is not part of this. That's not included. And then what type of cards do you have? You're going to have an ace. You're going to have a 2, 3, 4, 5, 6, 7, 8, 9, 10, and you're going to have a king, queen, and jack. So now that we know all about the different types of cards, the question was, how many 5-card hands can I get? And since order doesn't matter, we are going to take how many cards there are, which are 52, choose how many cards we want, which is 5. And again, practicing writing it in factorial form, 52 factorial over 5 factorial times 47 factorial. And if I put this in my calculator, it's going to come snag this. Okay, 52, choose 5. I end up with 2598960. So again, 2598960. Let me add my commas. So 2,598,960 different ways to get 5 cards in your hand. Now, let me do ones that are a little more specific. So let's say we want the following. How many ways can you get a 5-card hand with 2 kings and 3 jacks? How many ways can you get a 5-card hand with 2 kings and 3 jacks? So 2 kings and 3 jacks. Okay. So you want to kind of think about this in terms of the fundamental counting principle like we did the very first day of this chapter 12, because I want 2 things to happen. I want to get kings and I want to get jacks. So I'm going to take all the ways I can get my kings times all the ways I can get my jacks. Now, for my kings, how many kings do I have? I have 4 kings. And how many kings do I want? 2 kings. 4, choose 2 times. And how many jacks do I have? Well, 4 jacks. How many do I want? 3 times 4, choose 3. And I'm going to work that out. Okay. So I'm going to take 4, choose 2 times 4, choose 3. And I end up with 24. 24 different hands that will have 2 kings and 3 jacks. Now, last one of these examples, and then we'll move on to the worksheet. So last example, how many ways can we get, and so I'm just going to write, how many ways can we get 3 diamonds and 2 black cards? So I want 3 diamonds and 2 black cards. So my diamonds and my black cards. Okay, so again, how many different ways can I get my diamonds? Well, how many diamonds are there? Well, there are 13 diamonds, okay? And how many diamonds are we trying to get? We're trying to get 3. So this is going to be 13, choose 3, times black cards. Well, how many black cards are there? We have 26 black cards. And how many black cards do I want? 2. 26, choose 2. So this is how many of the diamonds I have. This is how many I want. How many black cards I have, how many black cards I want. And using the fundamental counting principle, I'm going to multiply these together. And so I'm going to be doing 13, choose 3, times 26, choose 2, and I end up with 92,950. So 92,950 different ways. So now I'm going to go over the worksheet, 12- 28 to 12-33. So this is 12-28. And in here at the top, they're talking about how the other day when we're doing permutations, order matters, and there was repeats not being allowed. And in this situation here, we're dealing with a new idea, combinations. Okay, and with combinations, again, this time order does not matter for combinations. Let me just get this refocused. Order doesn't matter for combinations, and there is no repetition. Again, so here's the formula for permutations. Here's the formula for combinations. Now we're going to see some of these are going to be permutations, some of these are going to be combinations, and we have to decide which. So 5 members of the Spirit Club have volunteered for the club's governing board. These members are Al, Barbara, Carl, Dale, and Ernie. The club volunteered for the club's governing, so the club volunteered for the club's governing board. The club members will select 3 of 5 members as board members for the next year. One way to do this is to select a president, a vice president, and a secretary. Another way is to select a governing committee of 3 where all members have the same title. So we have 2 situations here. In both cases, we have 5 people, and we are going to be choosing 3. Here, we're going to be choosing a president, a vice president, and a secretary. Okay, that's one situation. And in the other situation, all 3 members are going to have the same title. Okay, so for A, how many different lineups of officers are possible? This means a president, a vice president, and a secretary are chosen. Thus, Al as president, Barbara as vice president, Carl as secretary would be a different lineup than Al as president, Carl as vice president, and Barbara as secretary. So this one is going to be a permutation. I'm going to put P for permutation, okay, because order matters. And we have 5 people, and we are going to be choosing 3, so 5P3. And then I want us to also practice writing this in factorial form. So that would be 5 factorial over 2 factorial. And if I was working this out, my 5, my 4, my 3, my 2 factorial would cancel out with the bottom. So 5 times 4 times 3, that's going to be 60 different ways. Okay, and again, you could just put that in your calculator. Now we have the same group of people. We're still picking 3, but this time they're a committee. And so no one has any particular position. Order does not matter. So this is going to be a combination. And so this is going to be 5 choose 3, which is going to be 5 factorial over 3 factorial times 2 factorial, or 2 factorial times 3 factorial. So what you'll notice is this is my permutation. Here is the same permutation. And what I'm doing is I'm dividing out 3 factorial. 3 factorial is the 3 ways that these 3 people are, well, 3 factorial is how many ways I can order these 3 people, which is 6. 3 times 2 times 1. So when I work this out, I end up getting 10 when I put that in my calculator. So now looking at C, how many different lineups for officers are possible now if Felicia decides to volunteer for the club governing board? So now we have 1 more person in the club. We had 5, now we have 6. And now we want how many different lineups for the same 3 positions. So this is going to be a permutation. This is going to be 6P3, which is going to be 6 factorial over. Now I'm going to write 3 factorial here, but it's not this 3. It's 6 minus 3, which happens to be 3. And when I put that in my calculator and I do 6P3, I end up with 120 different ways. Now here, same situation. We have Felicia in the group now. We have 6 people. We now are still picking 3, but order doesn't matter. So that's going to be a combination, and this is going to be 6 choose 3, which is 6 factorial over 3 factorial times 3 factorial. And when I work that out, I'm going to end up getting, let me do that, 6 choose 3, I end up getting 20 different ways. Okay, so now on the next one, since there are more volunteers, the Spirit Club has decided to appoint another committee member. If a treasurer is added to the list of officers, how many different ways are there to select for officers? So again, we're going to be picking particular positions. So this is going to be a permutation. We still have 6 people. So this is going to be 6p, but this time we're going to be picking 4, 6p4, and that's going to be 6 factorial over 2 factorial. And when I work that out, that is going to end up giving me, just come and snag this one up here. Okay, 6p4, I end up with 360. So 360 different ways. So now the same idea, this time it's just a committee of 4. So that is going to be a combination. So we're going to do 6 choose 4. And 6 choose 4 is 6 factorial over 4 factorial times 2 factorial. These two need to add up to the top, which is 6. So when I do that one, and I take 6 choose 4, I end up with 15. 15 different ways. Let me make that a little darker. 15 different ways. Okay. So now let's look at the next page. And on the next page, compare the results that you got from each part of problem 12-28 when the roles were assigned. Permutations, and when there were no specific roles, which was combinations. So how do the number of combinations and number of permutations compare in each situation? Develop a conjecture about the mathematical relationship between permutations and combinations chosen from the same sample size. Are items chosen from N relating permutations, NPR, and combinations, N choose R. So what happens is, again, remember, N choose R is equal to, oops, let me get back to it, is equal to, let me focus it. NPR, which is the permutation, which orders them into groups of R, puts them in groups of R and then orders them in those groups. Divided by R factorial. That is the relationship. Now, this is equal to also N factorial over, and again, NPR is going to be N factorial over N minus R factorial. That's your permutation. And then I'm dividing out the R factorial. That's the order of the R items. And again, there's your formula. So now they want us to test this, calculate the number of permutations and the number of combinations of 2 items chosen from 6. So on this side, I'm going to do 6p2, and on this side, I'm going to do 6 choose 2. So 6p2, again, let me just practice writing it, 6 factorial over 4 factorial. When I work this out, my 4 factorial, my 6, 5, 4 factorial is going to cancel out, and I'm going to end up with 6 times 5, or 30 as this answer. Now over here, this is 6 choose 2, which is going to be this 30 because it is my 6p2, and then I'm going to divide out my 2 factorial ways to get those ordered groups of 2. So this is going to be 30 over, and 2 factorial is 2. I end up with 15 as that answer. So now calculate the number of ways to choose 4 items from 20 if order does not matter. So this is going to be 20, choose 4. And let me just write it in factorial form, and then we'll put it in the calculator. So this would be 20 factorial over. I'm going to have a 4 factorial and a 16 factorial on bottom. Okay. And when I work that out, I'm going to be doing 20, choose 4, and I end up with 4,845. So 4,845 different ways. Now, the next problem. In one state lottery, there are 56 numbers from which a player can choose 6 numbers with no repeats. The order in which the numbers are chosen does not matter. So order doesn't matter. They usually just list them in number order from smallest to largest. You don't have to have them in that order. You just have to have those numbers. So out of the 56, I know it's hard to see, that's a 56 there. Out of the 56 different ways, different numbers we can pick, we need 6 of them. So we want to figure out how many different ways can we get lottery numbers. So 56, choose 6, which is, and here, I'm going to write it on top of this. So I'm going to write 56, choose 6, which is equal to 56 factorial over 6 factorial times 50 factorial. And when I put that into my calculator, 56, choose 6, I get 32,468,436. So 32,468,436. Now my question part B says, what's the probability of selecting all those winning numbers? So in order to select those winning numbers, there's one set of winning numbers. So it's going to be 1 out of this number, 3, 2, 4, 6, 8, 4, 3, 6. And that's going to be my answer. So these last ones here, these 2 are dealing with cards. Okay, so it says in a game of poker called 5-card draw, each player is dealt 5 cards from a standard deck of 52 cards. While players tend to arrange the cards in their hands, the order in which they get them does not matter. So this one we actually answered in our notes. How many 5-card poker hands are possible? So this is going to be 52, choose 5. And when I did that earlier, we ended up with 2,598,960. Okay. Now this one here, it says in a deck of 52 cards, there are 4 different suits, each with 13 cards. How many 5-card poker hands have 5 cards from the same suit? So when I'm doing this and I'm trying to get from the same suit, 5 of them, remember there are 13 cards in a particular suit. So I'm going to have 13, choose 5. That's all the ways I can get one suit. There are 4 suits. So I'm going to take this answer and I'm going to multiply it by 4. 4 times this to get my answer. Okay. So I'm going to take 4 times 13, choose 5. And when I do that, I get 5,148. 5,148 different ways. And on the last one, it says, in a club consisting of 10 members, how many ways are there to choose a committee of 4 members if the club president must be on the committee, but the vice president cannot be on the committee? So since it's a committee, order doesn't matter. Now, let me just jot down some notes here. We're starting with 10 people, okay? And we want a committee of 4. And it says that the president must be in the committee. So I'm not really picking him or her. She's or him, or they're in the committee. So now I really have 9 people left. Now I also know that the vice president is not going to be on the committee. So I'm not going to pick that person either. So I have 8 people that I'm going to be picking from. So I'm going to have 8 people, and the committee has 4 people in it, but I'm not picking 4 because, again, the president is one of the people that has to be in the committee. So I'm going to do 8, choose 3, and that's going to be 8 factorial over 3 factorial times 5 factorial. And let me just type in 8, choose 3, and when I put that in my calculator, I get 56. So just remember the difference between combination and permutations. Permutations order matters and there's no repeats. Combination order does not matter. And again, there's also no repeats. So that's the end of today's lesson.